Hey guys, welcome to week 7, I think, or 8, whatever, if you count the week number 0. As you can see, we are veering from one subject to another. And today I would like to talk about abstract algebra. And you will see that we will talk about groups, rings, fields. Well, I'll dwell more on groups though. But before I go and start talking about group theory, you learn this material in any foundations of Algebra 1 or even 2, I would say. We have talked a bit about polynomials. Well, I didn't talk about irreducibility of polynomials, but you also talk about polynomials in foundations of Algebra 2, I believe. Yeah, I think so. And now, okay, let's get started. So I will start with something with the first thing that I want to do before talking about before discussing about groups and everything. I would like to talk about binary operations. Okay. What is a binary operation? Well, a binary operation, let me do a bit of theory. Let's call this star, or denote this by star, and you'll see what do I mean by that. On a set S, right, associates to each pair, let's say AB, of elements AB in S cross S, an element, and I'll denote this element by A star B. You see, this is the operation. And this will be in S. So, right, this is what it does. So you have this operation star, it takes a pair and will associate this A star B, where this star can be anything, any operation you want. You can add two elements, right? You can, multiply two elements and so on. Anyway, we'll see some examples. And now we're interested what kind of properties this binary operation will satisfy. So the first one we have in mind is the associativity. So a binary operation is associative if the following thing happens. If A star B star C is the same as A star B star C. These are the type of operations that you usually take for granted when you deal with positive integers or whatever, even reals, for all A, B, C in my set S, right? So this is what this is the associativity. Now we say that this is commutative. If A star B is the same as B star A for all A, B, and S. Let's see, what else do we have? How do we call this identity? The identity element, which says that if there exists an element, let's call it like this, if there exists an element, let's say E, usually we denote the identity by E in S, right? Such that A star E is the same as E star A and is equal to A for all A in S. This is what we call the identity elements. Moreover, if the identity exists, is unique. All right. how should we call this? The inverse element. Which says the following: if there exists an element B in S such that, let's say, A star B is the same as B star A, and moreover, this equals the identity E, then then B is, we denote this by A to the power -1. So this is the inverse element of A, right? Okay, so we have this. These are the main operations that you can do, that you can perform with with elements in, right? We're not even talking about group in a set, let's say. And now I'm gonna give you an example, and this was a problem. In fact, if you can tell me, this was a problem 1. Well, it's a Putnam A1 back in 2001. And the problem says the following. We'll consider a set. So consider a set X, right? And the binary operation let's say star on X. Now we assume that that A star B, everything star A is B for all A, B in X. Okay, let's write in words, right? Show that. We also have the other way around. It's A star B star A is B for all AB in X. All right, I want you to look at this very carefully. In fact, I would like you to tell me how we should solve this.
Couldn't we show it geometrically with like circles like on top of each other and things like that? Like for the different cases where A and B overlap and then they don't?
Maybe that's a good intuition, but I mean formally. You have to write this formally. I understand what you mean, right? So how would you approach it? How would you write this formally? So keep in mind that the binary operation between the two is defined. And when you define the binary operation between A and B, you can also define the binary operation between B and A, right? A star B and B star A. The only thing that you don't know that they commute. You don't know that this is associative. You don't know anything. You just know that there is a binary operation. So that's the trick. So you don't have too many options here, right? So the only thing you need to do is just to look at A star B or B star A, and maybe you can, and the only thing you know is this guy here. Keep in mind, that's the only thing you know. No, you're not allowed. You don't know if it has an inverse or not. You don't know anything, right? I just told you what it means to be associative, to be commutative, to have an identity element to an inverse element. Well, Nadia, don't be sad, because actually this would give you like not too much headache, because your options are very limited. You can just have like 1 or 2 options.
Well, couldn't we prove it's commutative because it's applicable for all A, B, and X? So if it's applicable for A times B, then it would be applicable for B times A when they are the opposite values of each other.
So, okay, be more specific. So you can say something here. So instead of basically saying, you can substitute, for example, for one element, you can substitute A star B or B star A. Well, you have a bunch of options. That's the only thing you can do. So what we should do? So look at this. Let's write it. So we know that.
Well, so if we can prove A star B is the same as B star A, then we can substitute it for C, and then C star A would be the same as A star C, wouldn't it?
Well, if you prove this, but that's a little bit going too far. Yes, it will follow immediately, but if provided that you show that. So what would you suggest? Just look at this. So we know that. So what do we know? We know that what? That, okay, let's write it again. A star B star A is B for all A, B, and X. So, and I have to come up with something to have the B star A on the other. So what should we do here? So if I substitute, right? Maybe what should I substitute? Let's see. Substituting. Maybe I should substitute B. Let's try B star A, right? For A. We have, what do we have? Let's see. So for A, so I'll have B star A. Let's be careful here with the operations. B star A star B, right? Star B star A, right? And we know that this is B, correct? So at first we know that this is B. But on the other hand, what do we know? This guy here inside is what? If we reverse this, this will be what?
That would be also B.
Be careful because
no, that'll be A. That'll be A. Yeah, that'll be A.
Exactly. This is A, right? So this will be nothing else than just A star B star A.
So how did you reach the conclusion that B star A, like you can substitute B star A for A?
Look, I just look at the, instead of A, I put B star A. So I replaced A by B star A.
Okay, but aren't you assuming then that B star A is in the set?
Yes, it is, because it's a binary operation. I said A star B and B star A are in the set.
Right. Okay.
That's it. You have only 2 options, A star B and B star A, to replace for A and B. Well, we have kind of 4 options. That's it. So that was a trick. That's it. End of story. Well, was it hard? That's the problem. I'm not kidding. That's it. It's over. All right, let me give you another problem. Problem 2 in a similar fashion. And I think this was a Putnam, I don't know what the Putnam. Yeah, I agree, the solution is very easy, but it requires a bit of thinking to substitute B star A for A, or maybe you can, why not substituting A star B for A, or something like this, you know? Anyway, so now let's see. This was a Putnam, God knows, I think it was Putnam A3 1972, but I might be wrong, but I'm sure this is for 72. It says the following. Let S, so again, we'll consider a set S be a set, right? And star will denote, again, star, a binary operation. Right? So this is a binary operation on S satisfying the following laws. And the first law is given by X. You see now I have some conditions now. I'm going to get a little bit more complicated. X star Y is Y for all X, Y, and S. And the second condition is that Y star X, okay, this is Y for all X, Y, and S. Well, now we have to show the following. Show that star is commutative, so this binary operation is commutative. But not necessarily associative, but not necessarily associative. All right, I want you to look at it. So basically, you have to show that that X star Y is the same as Y star X. So you need to look for something here. So it's the same in the same fashion as the previous one. Try to think of it for a couple of minutes. You can come up with some ideas. Again, try to look for something like using those two laws instead of, keep in mind, again, when you have a binary operation, you're allowed to look at X star Y and Y star X. That's it. You don't know anything. You don't know it's commutative. You don't know associativity. As you can see, you have to prove it's commutative. Once you have these two laws, this will imply that the commutativity. So, but other than that, you don't know anything else. So you have to try something. Maybe let's use the first law. So let's replace, well, so what we're going to do is the following. Using law, so the first one, so keep in mind, in fact, let's write it again so that you can see it better. So it's X star Y is Y. So using this first law we have, and now we have the following. So let's see. Because I also want to, so we have that, let me see, Y star X star Y, right? Right. Okay. So this guy will be, and it's X star Y star X star Y. Right? right? Using the first one. Because you see, right? That's it. Okay.
So you just added x star y to the side of it. Right?
Yeah, exactly. You see this guy here, this guy is y. So I'm doing this trick here. And now I'm trying to play a bit with it, right? So this guy is, okay, this guy is y. And now I'm trying to play with this a bit. Now I want to use, I have this. So maybe now I should use the second law. So using the second law, what do we get? So let's see, we have y star x, right? And look at the, so how should we, y star x, so it's y. And now we should look for, so what do we get? So we get that x, now let's look. So this will be x, in fact, no, let me, oh my, so let's see. We have, okay, let me write like this. So it's x star y, right? So using this second law, let's, in fact, let me write the law so that I can see it. This guy is y. So using the second law, let's write it here so that we can see it. X star y star x is y. So we have this law here. Let's oops. And this one here. Okay, so once we have this, so we have this x star y. This will be what? Can you tell me using the second law? You see, instead of y is x, and instead of x is x star y. By the second law, what do we have? This equals what? What is this equal to? Look at it. You see, instead of x, you can take y star x, x star y, and you can play around. This will be, look at the second law. This will be x. Is the second law applied for instead of y star x, we have x, and instead of x, we have x star y. And when you apply the second law, you have x. Okay. So what do we obtain? What do we obtain? Can you tell me? Y star x star y is what?
X.
Exactly. All right, so we have these informations. So let's hold this here. We have this piece of information. And keep in mind that we have to show somehow the commutativity. And now I think we're on a good track because let's look at what? Let's look at y star x. And at some point we have to show, we have to apply some of the identities which will in some way will obtain that y star x is the same as x star y. So what should we do now? So this will be y star, and now instead of x, we can put this, what? We can put this y star x star y. Okay, and this will be further equivalent to what? Can you tell me? By one of the laws is what? This is what? What is this? y star
So y star x. Or wait, no, yeah,
is what?
that's not useful.
So y star x, y star x, y star. Yeah, what is this? Look at one of the laws and try to look there. So which law? Okay, let's look. If you look at law number law one, right? You have instead of y, you have y star x, right? Does this follow by law one? Look at law one. So instead of x, you have y, and instead of y, you have x star x. So this will be what? By law one will be x star y. Just look at it. Right? Anyway. So y, look inside law one. Y, x is y. You see it here inside as well. And y is x star y. And we know by law one that x star, just replace x by y and y by x star y, and you will get exactly this. Anyway, so this will prove the commutativity. So it follows that which proves the commutativity. And now let's see for the associativity. So we're done with the first one, but not necessarily associative. When he tells you not necessarily associative, maybe you should come up with an example or something. So now we want to prove that this is not necessarily associative, so we can come up with, so let's consider, so for the associativity, let's consider S, and I'm going to take S to be as simple as possible, to be the integers, the set of integers, endowed with the following, with the following operations, with the law, let's say. And with the law I'm going to endow this set of integers with will be x star y will be, and I want you to pay attention, negative x minus y. And I want you to tell me, do you think it's associative? Well, let's see. We have that x star y star z, this will be equal to what?
Negative x minus y, and in parentheses, minus z.
So negative x minus y, in parentheses, minus z, correct? Okay. And now let's see, okay, now what is this guy? X star y star z. This will be what? Can you tell me?
Negative x star parentheses negative y minus z. Or not star, sorry.
Minus.
Yeah, minus.
So negative x minus parentheses, wait, let me. So tell me again, so it's negative x minus negative y minus z, right?
Yeah.
Which will give us, whatever, so it's negative x plus y plus z, correct?
Yep.
And this will be negative x, negative y minus z. Well, when these two are equal, I'm gonna kill myself. So for example, if you wanna, for example, if you pick, okay, for example, you can pick the simplest numbers possible. Just take x equals 1, y equals 2, and z equals 3. We have that what? This guy, so 1 star 2 star 3, by our operation will be -1, -2, -3, whatever this is. So this is -6, and 1 star 2 star 3 will be what? Will be -1 plus 2 plus 3, which is not -6 as far as I'm concerned. This is 4.
So does the binary equation that they gave us have to apply for every binary equation possible?
Yes, you can do
I see.
binary anything you want. So that's the only thing. And you, of course, you have to obey these two laws. Well, I was asked a question here by Timothy. Let's see. Why did you choose that? Well, magic. This is how, when you try to prove, look at the statement of the problem. It says, show that this is commutative, but not necessarily associative. When you have this kind of questions, you always think of a counter. Well, when you want to show that this is commutative, you prove it. And this is what we did. Using those two laws, we proved it. But when it says like, but this is not necessarily associative, okay, all right, so maybe I should just provide an example to show that it's not necessarily. And there you go.
But if we apply the endowment you set as y star x equals -y minus x to the laws, does it work out?
Yeah. Well, to these laws, yes, absolutely. Yes, absolutely. So you'll show that this is commutative. So there is no problem with that about it. Anyway, so this is the main trick was to consider this. And the set Z and this. All right. I think these are the two examples, and I want to veer towards something else. So this is the first part with binary operations. I think you got the gist. I think it's just manipulation of things. Now, the second part that I want to talk about is about groups. So now we will put some structure on, and now let me start with the definition. I want to give you the definition. You'll see, well, you learn this kind of things in a, like I said, in a Foundations 1 of Algebra course. So you'll take this, well, usually you will have to take this in your senior year or Foundations 2. Did anybody take Foundations of Algebra 1 or 2 except Jack? Did you guys take it? Any of you? No, nobody. Huh? No, okay. So probably you'll take this in your junior or senior year. All right, so let's see. Let me give you a philosophic definition of a group. What is a group? So a group, and then I'll give you the formal definition as well, is a set of transformations right, of some space it's a group with one object, yeah. Okay, yeah. So this is what Dimitri taught you. So you learned this in the category course, Jack?
Yeah.
Yes, that's correct. It's a group with only one object. All right, so this is a set of transformations of some space that contains the identity transformation. Right? And it is closed and is closed. This is important. Okay, in fact, it's closed under the operation of the, well, closed under composition. And under the operation of taking the inverse. Of taking the inverse. Okay, and now we can can give a formal definition as well. So a more abstract definition of a group is the following. And for example, let's say a set G, and this G, I will endow this with endowed with a binary operation, and this binary operation will satisfy some law. With a binary operation, I will denote this a binary operation by the dot this time, because I don't want to deal with star. Is called a group, right? If it satisfies the following operations. And you will see that all those operations, all those binary operations that I gave you at the beginning must be satisfied by the group. The first one, associativity, which says that, well, I'm gonna x dot if you want, x dot z, but usually you don't put the dot, so it's the same as x dot z dot, x dot y dot z for all elements x, y, and z in G. So this is what associativity is. The second one is identity element. So a group satisfies this. So you see in a group, you have much more freedom to operate with elements. So in other words, this is that there exists this element E in G such that x dot E, if you want, is E dot x and is the same with x for all x in G. Usually we don't put this dot, but anyway. And the third one is the existence of an inverse. And this inverse, right, says that for every element x in G, okay, this is G here, not 6. So for every element x in G, there is, or there exists, let's say this element x to the power -1, so x inverse, right? Right, in G, such that x dot x inverse is x inverse dot x and is the identity. Well, right.
You said the dots normally not included in the notation.
No, you don't. So when you don't see them, when I say xe is ex and is x, or you can understand that this is the dot operation on the group, right? Now let's point out some remarks here. And the first remark is the following. A group is called abelian or commutative. As you can see, I did not include in these three operations the commutativity. So a group is called abelian, or in fact, let me say commutative. Right? If, guess what? xy is the same as yx. You see, I'm not including the dot here, but you can say that x dot y is the same as y dot x for all x, y, and g. Right? So this is what we call an abelian group. Another important thing is a group is called cyclic. right? If it's generated by a single, if it is generated by a single element. This is what we call a cyclic group. That is, and let me just say, that is, if it consists, and that is if it consists of the identity element and powers of some elements, and powers of some element. Right? That's what we call a cyclic group. And now another thing that I would like to say, the order of an element in a group, this will be important because we will talk about what happens to the order of an element in a group. So the order of an element, let's say G, we'll take the small g, and this will be in a group. Okay, let me write in words. In a group G, right? So the order of this element G in a group G, and we denote this by, denoted by, and I'm going to write it this way, or of G, right? This is the order of an element G, is, in fact, is the least positive integer n such that, guess what? G to the power n is the identity. So that's what we call the order of an element G in a group, right? And we'll give some examples. And here I would like to point out a remark, very, very important, and we will use this. This is, like I said, very important. If G is a finite group, right? And make sure you see this word finite here. Then we have that the order of G of this element will divide the order of the group, and we'll denote this by this. So the order of the element divides the order of the group. Keep that in mind. This is important. Always this happens when you deal with a finite group, right? Okay. And now I would like to talk a bit more. I have, oh my goodness. And then I have to do an example. Maybe two. Anyway, now I would like to talk a bit about subgroups. And I want to tell you about Lagrange and Cauchy's theorems. But before I will tell you about this, let me give you the definition of the subgroup. All right, so let's consider G, let G be a group. And in fact, let me write it in this way so that you can see it. So I can write it in this way. So I know that G is endowed with that dot. So this is be a group. So when I say a group, you already assume those three operations, right? And I'm gonna take this H to be a subset of G, right? And now I want to see what happens when the subset is a subgroup. So we say that H is a subgroup of G, right? If for all X, Y, and G, it follows that X, Y inverse is in H, right? That's the rule for the subgroup. Keep this in mind. So in other words, it's or you can write this in two ways if you want. You can say that for all X, Y, and G, then X, Y is in H, and then for all any X in G, then X inverse is in H. And the way we're going to write this, so we write H is a subgroup of G as in the following way: H less or equal than G. That's how we write it, right? Also, let me tell you that H is called a proper subgroup of G if H cannot be G. You know, sometimes the subgroup can coincide with the entire group, so we don't want that. And now the first amazing, astonishing theorem that comes, and you learn this in any Foundations 1. Jack, you learned this in Foundations 1, I believe, right?
Yeah.
This theorem is due to Lagrange, which says the following. Basically, if I have a group and I have a subgroup, then the order of the group, the subgroup will always divide the order of the group. So let's write this. So let's consider let G endowed with this operation be a finite subgroup. This word finite here is important. Be a finite group. And we'll consider an H is a subgroup of G. Okay? Then the order of the subgroup will divide the order of the group. So let's write this. So you can write in the following: order of H divides the order of G. Right? So as you can imagine, the order of the subgroup is the order of all those elements that raised to the power m will give you the identity, right? All right, and now the let me give you another theorem. Probably, I'm not sure if this was taught in Foundations, but you can tell me, and we'll talk about the consequences of this theorem. I think the consequences are much more important. The theorem of Koshi, and I'm going to state it in this way. Let G be, again, a finite group. Again, as you can see, the word finite here, I want to stress this out. So be a finite group, right? And we'll consider this, and P is a prime number. P is a prime number. Such that, and we'll have this condition. P will P divides the order of G. So let me write this more. P divides the order of the group G, right? Then, guess what? There exists an element of order P in G. Then there exists element, let's just say X in G, such that the order of X is P. So in other words, such that X to the power, in fact, no, let me restate it because I restated as a consequence that I didn't want to. Sorry about that. Let me see. Okay, then, okay, let me write it. Let me restate it in this way and then equivalently. Then the number of solutions of the equation and X to the power P equals the identity is a multiple of P. In other words, if we have some consequence, and now I'm just going to write some consequences. So I want you to look at the theorem. So consequence 1 is the following. If G is a finite group, and P is a prime number, so is a prime such that P divides the order of G, right? Just like in the theorem, then there exists an element. There exists an element. Let's say X in G, such that X to the such that for the order of X equals P. So that's the first consequence, and the second consequence number 2, again, if G is a, so G not 6, why? So if G is a finite group, and P is a prime, such that P divides the order of G, right? Then the number of subgroups right? The number of subgroups of order P is congruent with 1 mod P. With 1 mod P, and we have seen what this means. Mod P, right? It's important to have a finite number of elements in that group, because if you have infinite elements, it's very important to be finite. Because it holds true only for finite groups. For infinite groups, it doesn't hold true. All right, now let's see some problems. And the first problem that I have in mind, well, I still have like 20 minutes plus some extra time, so probably I'll go over time because I want to do some problems. Let me see. So let's see, problem, I think it was problem 3. This is a very classical problem. I think I put it in the worksheet as well, but I would like to do it. Let G with a dot be a group such that xy squared is the same as x squared y squared for all x, y, and g. Show that G is a billion. All right, I want you to look at it, and then we'll do another problem where we actually see how to apply Lagrange's theorem. And perhaps maybe I'll do one more problem with some operations in a group. All right. This is actually very simple. So what do you think? How would you approach this? Well, let's look at this guy here. So let's explore this. This is what we want to do. So we know it's a group. So keep in mind, we also know that this is a group. So we have those three operations, and we want to see what happens to these operations. So keep in mind, a billion means that xy is yx for all x, y, and g. Anyway, you see, in this problem, I didn't even put the dot. So, but you can imagine that that the dot is there. So that's why sometimes it's there, sometimes it's not there. But all right. So how would you approach this? So let's write. So we have. Let's look at this guy. X, y, everything squared. This is what? Pay attention here. We don't have as much freedom as we want. So the only thing we can do, we can write this as xy, xy. Keep that in mind. And now what can we do? And we know that this guy is x squared, y squared. So we know this. For all x, y, and g. So let's, let me rephrase this. We know that. So what would you do here? I'm curious.
Multiply by the inverse of y.
Exactly. So we can multiply by the inverse of y. Okay, I'm going to write it in this way. xy is x squared, y squared. To the left, to the right, because this is important. I didn't say the group is a billion. We have to show that.
To the right.
To the right. Or to the left.
Or on the right. On the right side.
What do you mean? Oh, here?
Yeah.
Why? By the inverse of x?
Of y.
Ah, of y. Okay, yeah. We can do this, or the same thing. Okay, you said y. You multiply by the inverse of x here, right? It's the same thing as Jack said. All right, so we have. So what do we have? So we have x inverse x, and we know that this is a group, so we can associate them any way we want. Y, x, y, x inverse x squared, y squared. So we can associate these two. This will give me the identity element, and this will give me the element x. So this will be equivalent with y xy equals xy squared. Now what? Can you tell me what should we do now? Well, what Jack said, we can multiply by y inverse to the right. And we have, what do we have? We have, pay attention, I multiply to the right. So I have y x y y inverse, which is xy squared y inverse, which this is equivalent if you look at it. So we can associate these two in any way. So this will be the identity. So it'll be yx equals x, and this guy will give me y, which is exactly what we wanted to prove. That's it. Game over. Problem's done. It was very easy. This is like a Putnam A1 type of problem, but I think, Jack, did you have this problem in your homework or something like this?
Yeah, I think this was in our homework.
Yeah, it's
for Foundations 1.
yeah, it's actually even a homework problem for Foundations 1. Okay, now let me do something similar but a little bit more involved, and you'll see what I mean by that. I wanted to do this easy problem because I want you to see how to operate in a group. But I'll give you, I want to do 2 more problems. So problem 4, let the statement is the following: let G be a group such that x squared is the identity for all x in G, right? Okay, the first part, which is easy, and show that G is a billion. And when I say a billion, I say commutative. Keep that in mind always. Well, when a billion commutative, it was given in the honor of Abel, Niels Abel, the Norwegian mathematician. Also, you have heard probably these days about Abel Prize. Oh, again, this is where it comes from the German mathematician Abel. Show that G is a billion, and moreover, if G is finite, it's a finite group, then there exists let's say k, a positive integer, k, such that the order of the group G is a power of 2. Wow, this is what happens. So when you have a group which x squared is this guy, well, of course it will imply it's a billion. But moreover, it will imply that the order of the group is a power of 2. So as you can see, because as you can sense here, you can use the maybe Lagrange or Cauchy's theorem. Well, I would say one thing. I'm not going to do the first part. Show that G is a billion. I'll leave it to you as an exercise. I think this was another homework problem in Foundations 1, right, Jack?
Yeah.
I'll leave it to you. It's very similar to what we previously proved. It's basically the same idea, right? So you know, you can just, let me give you a hint. So you know that x squared is the identity. You can multiply to the left, to the right, doesn't really matter, by x inverse. So you know that x is x inverse for all G. And now you know that, well, instead of, you know that x, since x squared is the identity, you know that xy, everything squared, is the identity. And now you can operate this. You write xy, everything squared as xy, and now you can multiply by x inverse to the left, then by y inverse to the right, and then you'll derive this. You'll derive the commutativity. So you'll derive that xy is the same as yx. It's the same thing as you have seen in the previous exercise. So I'll leave it to you as an exercise. So now I know that at this point this abelian group G is, so I know that the group G is abelian, and I want to show that moreover, if this is a finite abelian group which satisfies that x squared is E for all x in G, then the order of the group G is a power of 2. So how should we prove this? So let's assume by contradiction that the order of the group G is not a power of 2. So let's assume this. Then there exists a let's say a prime number right? Let's say P, the odd prime number, let's take P greater than 3, such that P will divide the order of G, right? That's obvious. Since it's not the power of 2. All right, and now guess what? So now we have this. I want you to look at the consequence of consequence 1. What does it say? Of Koshi's theorem. Since I have a prime that divides the order of the group, right? So by the consequence 1 of Cauchy's theorem, what do we have? Let's say we obtain the existence of an element, let's say A in G, right? Let's call it like this, such that with, let's say, the order of this element equal to P. Right? This is consequence 1. Look at it. There exists an element such that the order of that element is P, right? All right, that's beautiful. And now, what does this mean? Well, this means that since the order of the element is P, and by the definition of the order of an element, this means that A to the power P is the identity, right? We said this. But we also know that A squared is E. So this implies that what? That A to the power, the JCD between these two, A and, A to the power JCD, sorry, P and 2 is what? Is E. Or equivalently, A to the power with the JCD between P and 2, since P is greater than 3, is an odd, is 1. So this means that A to the power 1 is, so this means that A is the identity. That's false. Cannot be, right? The identity. So in other words, so we assume by contradiction, where did the contradiction come from? That the order of G is not a power of 2. So this implies that there exists a positive integer n such that the order of G is nothing less than just 2 to the power n. Wow, and that's it. All right, in the remaining time, I know I'm a little bit, let me do another problem, like Putnam problem. So problem number 5, and then I'll stop. I wanted to show you an application of Cauchy's theorem. I think that's important. This was a Putnam B3. in 1972, which says the following. So a group has elements G and H. So this time is G and H, not A and B. These G and H satisfying the following laws. Okay. GHG. So as you can see, I don't put the dot there. So GHG is the same as H G squared H, right? G cubed is the identity. I'm going to denote this by 1. So 1 is the identity in the group. And the last one is that, so this is the first condition, the second one, third one, that H to the power n is the identity for some odd n. So for some odd n. Prove that H is actually the identity. Okay, I want you to look at it. Again, you have to play around with some with the operations in the group, and we also with these three operations. So let me give you, in fact, let me just give you the main ideas. And I'll leave this to you as an exercise to, so the main ideas. Because indeed it has some idea. Well, when you look at the first condition, this should ring a bell a bit. And maybe you should prove almost some kind of commutativity between G and H squared or G squared and H. So I would say the first prove that GH squared is the same as H squared G for all G and H in G. So that's the first thing you need to do, right? And now, once you do this, maybe you can proceed in showing also, secondly, show that, let's see, what else? So I want to show that H is 1. Maybe show that actually even more happens. GH is HG, right? And also by using the third, well, a combination of all these three together. So once you use also this and this, you can show that, what else? So you can show that H equals H squared. So once you have all these, once you show this, then I think you can conclude that H will be the identity, right? So from here, you can actually conclude that H is nothing else than just the identity. These are the main ingredients. So you have to be careful on how to explore all these three conditions given in the problem, and of course the laws of the group. Because keep in mind we have a group here, right? Do not forget that. So we have some other three laws, and you have to play around with these. Okay, I think I'm gonna stop here for today. Thank you very much. Well, I will meet on, well, I was planning to discuss another problem, but probably I will do it during the recitation. We'll meet on this Thursday. We'll discuss some previous Putnam problems. You will see that in my list. We start a new worksheet, and I will send you an email on which problem to think about. Okay, guys, thank you very much.